first talk. We just have 2 talks today and full tomorrow, and full to the extent possible the day after tomorrow. Of course, we're all grateful to US taxpayers who provide support to National Science Foundation, which has selected our session to be supported. Okay, and the first talk today is by Markus Lange from Aachen. He is going to speak on accounting solutions to differential equations.
Yeah, thanks for the introduction, Alexei, and thanks for putting together this opportunity for me to talk and to listen to other talks. So, yeah, I'm concerned with polynomially nonlinear partial differential equations, and I'm particularly bad at solving them. So if I have some system of differential equation like that, I have no idea what to do. I plug it into Maple. Maple returns some set of solutions, and I have to trust in Maple. Whether this is the complete set of solutions or whether some solutions are missing is a mystery to me, or at least it was a mystery to me. So the motivation of this talk is if I have a given set of solutions returned by Maple or some other computer algebra system, I'm interested in whether this is a full set of solutions. So whether an equality between sets of solutions of differential equations hold. And the goal, or how I want to tackle this problem, is by measuring the size of the set of solutions. First, with the dimension polynomial, or a slight generalization of Colson's dimension polynomial, and second, I introduce a new measure, the differential counting polynomial. I should always say what kind of solutions I'm thinking about, and I'm thinking about formal power series solutions or analytic solutions, so local in any case. Why do I do it? Yeah, it's easy to make power series ansatz to solve a system of differential equations, or in this case, Burger's equation. Just evaluating the equation at 0 yields some constraint for some power series coefficient, and of course I can differentiate the differential equation to get more constraints. Then I have some free power series coefficients in the green area here, and the red area, these are uniquely determined once I fix the green coefficients. Colson suggested to count the number of free coefficients in the following way: just say that there are, in this case, 2L plus 1 free coefficients up to order L. And this is the idea that led him to the differential dimension polynomial. And in general, how do you go about this? You represent your system of differential equations by a radical differential ideal. Then the number of free coefficients is just the dimension of the residue class ring of this differential ideal. And there is this nice base theorem that every radical differential ideal has a finite prime decomposition. And so what we are about to do is look at each prime component separately. And Colson was able to prove the following theorem. Given a prime differential ideal, then there exists this dimension polynomial, and this polynomial describes the number of free coefficients, at least alternatively. There are further properties not that important to this talk, mainly concerning invariance under differential birational maps. And to me, most important is that you can use the dimension polynomial to compare prime ideals or their solution sets. Namely, if I have 2 prime differential ideals contained in each other, then they are equal if and only if their respective dimension polynomials are equal. So you can think of J describing the solutions you are given by Maple or Mathematica or whatever system you have, and I to be the prime differential ideal describing the complete set of solutions. Okay, yeah, nice theoretical result, but not exactly algorithmic, because at least I don't know of any implementation giving you this prime decomposition of a differential ideal, but there are other algorithms doing similar things. I have implemented a decomposition into so-called simple differential systems. This is a Thomas decomposition suggested in the 1930s by Joseph Müller-Thomas. It just takes a system of differential equations and introduces suitable inequations and new equations and gives these simple systems.
You can do prime decomposition, but not necessarily minimum.
Yes. But I haven't seen an implementation of that.
Oh, yes.
It would be very expensive to implement it. Yeah, and the minimality is another problem.
Maybe not to implement, but to run it.
Yeah. But so there were other algorithms to decompose a radical differential ideal. This decomposition to simple systems into characteristic sets, into regular differential systems. And they have one thing in common. Each of these systems induces an ideal, the so-called characterizable differential ideals. And it turns out this theorem holds for characterizable differential ideals. So still there is this dimension polynomial. The invariant conditions still hold for characterizable differential ideals. Yeah, and comparing inclusions of differential ideals is slightly more tricky because the dimension is made or is actually defined using prime ideals or chains of prime ideals. So you need some additional information, and in this case it's just looking at the degrees of the equations in the systems, or to be more precisely the degrees in the leaders of the equations in the system. So now we have several algorithms and implementations to compute this dimension polynomial. We don't even need to go to the prime decomposition. And yeah, algorithmic is always nice. So now Berger's equation is just the number of free coefficients is 2l plus 1. What does Markus say? It gives a set of solutions involving three free coefficients, and this is certainly not the complete set of solutions. I should defend Maple in a sense because first, Maple is, to my experience, the best computer algebra system in solving these differential equations, and secondly, probably there aren't any more closed solutions to this differential equation. So I wouldn't expect Maple to return more solutions, but still it's good to know that there are no more solutions, I guess. Or the example I used in the beginning, if I run a Thomas decomposition onto the system, I get two sets. So here you see that the Thomas decomposition introduces inequations, and each of these simple systems, you can even see that these solutions obviously belong to this second system. And each of these systems now gets assigned a dimension polynomial, and we see that the larger set of solutions is not returned by Maple, but the smaller set or more obvious set is.
But you will get the same from a characteristic decomposition.
Yes, you will get the same from a characteristic decomposition or from a decomposition into regular differential ideals. Yes. So yes, I still have a problem with that description, which I can solve, but which leads into new problems. And the first problem is I would like to have a description of this set of differential equations and not the two sets I have below here. So because dimension polynomials are obviously not additive, so I have to look at the dimension polynomial for each of these characterizable ideals. And my second problem is it's in a sense rather imprecise, because you wouldn't dare to describe an algebraic variety just by using the dimension. You would like to have more information about the variety. And yeah, the way I started to go about this problem is by introducing a counting polynomial, in this case the differential counting polynomial, to give a more precise description. It's actually coming from group theory, the idea, introduced by my advisor, Professor Peskin there, and I call it the algebraic counting polynomial to distinguish it from the differential one, and it counts constructible sets, i.e. sets given by polynomial equations and inequations. So okay, how do you count a set? The first axiom is if the set is finite, just take the cardinality. What to do when the set is infinite? You need some description of an infinite set. And what you can do is say the affine 1 space has counting polynomial infinity. Infinity is just a formal symbol in this case. So a term like infinity plus 1 or infinity squared or 2 infinity makes sense to me. The third axiom actually solves my first problem, because if you have a disjoint decomposition, you get a sum of counting polynomials. And the last axiom is the most interesting one, I guess. So if you have a fibration, i.e. f projects down onto B, and each fiber has the same algebraic counting polynomial, then the counting polynomial of f is just the counting polynomial of the base times the counting polynomial of one fiber, which means any fiber, if they are all the same. So you might think of a Cartesian product, and then the Cartesian product yields the product of algebraic counting polynomials.
Is it related in any way to some model theoretic notions of dimension?
I don't know.
Maybe Omar can say.
Well, it would seem something like Morley rank, but I think right now it's not totally clear with just these four axioms. Yeah. But I mean, the first one is Morley rank of finite set is 0. So.
Okay. So for the fourth axiom, you can also think about unramified covers. And I think this is just an easy example. I want to show you how you compute the algebraic counting polynomial and what it means. So if you have a ramified cover here, then for the fourth axiom, you need to take out the ramification point. So by the third axiom, you can just write it as a sum of the curve without the point and the point in itself. The counting polynomial of a point is 1. Now you have an unramified twofold cover of the affine 1 space minus a point. So this is 2 times the counting polynomial of the affine 1 space minus a point. Yeah, and now the affine 1 space has counting polynomial infinity. You take out the point, so you subtract 1, and this is 2 times infinity minus 1. So it's also easy to see. You have a twofold cover, and 1 point is double, so you have to subtract it once. What are the properties? It's well defined in the sense that it doesn't depend on the decomposition. It's algorithmic. So there is an algebraic version of the Thomas decomposition that somehow does what I did in the example, makes polynomials square free and so on. And it generalizes the dimension, because the degree of the counting polynomial in the indeterminate infinity is just the dimension. So it makes sense in this example, I guess, because this is one dimension and the degree is 1. But for me, the most important property is if I have 2 constructible sets contained in each other, then they are equal if and only if their counting polynomials are equal. And this is basically the theorem I would like to have for differential equations. Okay. How do you introduce this counting polynomial for differential equations? Just look at the ideas from the dimension polynomial. There, you just looked order by order and took the dimension up to this order. And now the idea is the same. I will go on order by order and take the counting polynomial for each order. Or the counting polynomial for the power series coefficients, to be precise. Okay, so now I have to define it. And it's defined in the algebraic case using this decomposition. And it turns out in the differential case it's not that easy to decompose all the constraints for power series coefficients. All I could show is that there is a suitable decomposition, but it's countably infinite. I will justify that later, why this is necessary. I don't specify here the kind of technicalities in which sense it's countably infinite. But to somehow work with these countably infinite sets, I use the fifth axiom. So if you take an F11 space, remove a countably infinite set, then you have to say what kind of counting polynomial you get, and you take infinity for the F11 space and Aleph naught for the countably infinite set. So Aleph naught is the second formal indeterminate here. Okay, using this, I first define the eighth differential counting polynomial. By just taking all constraints I can collect for the lower power series coefficients and computing this decomposition, applying the axioms. This is a polynomial in infinity and Aleph naught. And if I get a closed form of this polynomial, then I call it the differential counting polynomial. Actually, all examples I've seen had a closed form, but I was not able to show that there was always a closed form. So how does such a closed form look like? I just write down the examples. You will see the differential equations for these counting polynomials later in my talk. So the order L might appear in the exponent, or the order L might appear in the coefficients. And there are examples where this Aleph naught actually appears, so where some countable phenomena appear. And actually this is the first example I would like to show you. So this is a system of two ordinary differential equations, and the solution set is something of dimension 3. I guess you would suspect this. Here we have an equation of order 2, and here we have one of order 1. And you have to take out something of order of dimension 2. This comes from this, because V is not allowed to have a zeros coefficient equal to 0. Yeah, and now we have two additional terms, so there is now something one-dimensional hidden in this set of solutions minus something countable. So you might suspect this is something algebraic. I'm working with formal power series solutions, but actually all of these solutions are analytical, i.e. locally convergent. You can even compute the radius of conversion, because if we center the power series extensions around T0, then it's just the absolute value of T0. So I guess the theorem with the countable infinite decomposition is the best you can hope for in this case, because there are examples with a countable infinite exceptional set, and you have to incorporate them in a sense. I have some more bad news about the differential counting polynomial, and then afterwards I would like to try to tell you that the bad news aren't that bad as they sound at the beginning now. So what are the bad news? One can show that computing the differential counting polynomial is not algorithmic. That's actually the thing I didn't really like. Right. The second problem is, Hilbert's hotel. You have a countable infinite set, so you can shove points in there or get them out, and you still have a countable infinite set. So, the differential counting polynomial cannot be unique. So any Aleph naught can spawn plus or minus ones or something like that. And it's not even clear that any choice of decomposition you are taking so yields a finished differential counting polynomial in the end. So this is somehow related to the part that it's not algorithmic. So you really have to work by hand to get the counting polynomials.
So the last one says that it depends on the presentation of the...
No, it doesn't. So if Aleph naught doesn't appear in the counting polynomial, then it's unique and doesn't depend on the presentation. But I don't know that each presentation I take will end in a counting polynomial, actually. So you might need an infinite amount of steps to compute the counting polynomial by your presentation you've chosen.
What do you mean by presentation?
So you decompose the set of solutions disjointly, and this is what I mean, or what I understand.
It's a constructible set, you take unions,
yes.
And then it depends on the...
So you might make bad choices that don't lead anywhere, because it's not algorithmic. So now I would like to show that it's more unique than you might expect, and that there are large classes of examples for which you can give a closed form for the counting polynomial. And the first is a result about the uniqueness. You recall the algebraic counting polynomial had the dimension as its degree, and here the differential counting polynomial also has a degree. The degree might involve my order L, and now this is just the dimension polynomial under the suitable conditions that everything is given by a characterizable differential idea. So you at least have uniqueness on the leading term. Actually, you have more uniqueness because it's unique if Aleph not doesn't appear. Coming to examples, so there, I think this theorem is really important for the differential counting polynomial, but it's rather dry formulated. Afterwards, I will show on examples why this is important. So you've seen that these simple systems had inequations, and they are necessary to get disjoint decompositions, and these inequations describe what you are allowed to do and not allowed to do more than a characteristic set or a regular chain can. And if no such inequation appears in the simple system, then you know more. Then the counting polynomial is just given by a monomial. You already know the degree. It has to be the dimension polynomial. And then it's easy to show what the coefficients needs to be. It's just the product of the degrees. So it's you had to use the degrees for the comparison in the dimension polynomial, and now these degrees appear again here. So why do I think this theorem is important? Because many differential equations fall into this category. For example, Burger's equations we had seen before. But actually, any semilinear system of differential equations with that is involutive or completely integrable or whatever you might call this phenomena satisfies the conditions of this theorem. So the theorem yields, I don't know, the Cartesian-Stokes quadrilateral.
The simple system means?
Simple system is this is the system you get from the Thomas decomposition.
This you recall the definition?
Not in a short way, but it's quite similar to the characteristic sets. It's just you have a stricter definition in the sense of inequations, because now you need to make sure that the separand is not just saturated out of the ideal, but that the separand is really non-zero. And similarly for the initial also has to be non-zero.
And what about coherence?
And coherence, of course, yes. But the difference is that separands and initials need to be non-zero.
You mean like a scalar non-zero, or only like a?
It means the function is not zero.
I mean, but isn't that always the?
Maybe saturated.
Usually you only saturate, but you don't exclude that the solution you saturate out of the ideal is still in the closure.
But then how about term ordering? Because you have a degree. How about which ordering you use, which ranking you use?
For the computations you need an orderly ranking.
But then you have a degree here, so that means it's unique somehow.
Yes, it's this is not unique. Oh, I should have mentioned that in the beginning. Yes, that's a good point. So I don't really care about uniqueness in a certain sense, because for comparing solution sets, I choose one ranking, I choose one representation of the equations, and everything I do is in this representation. So these degrees are not unique, so you get other degrees. You will even get other dimension polynomials if you change your representation. But if I have my both solution sets and their dimension polynomials with respect to the same ranking, with respect to the same order, and so on, then this is not a problem for me. Thank you. That was a good point. I forgot to mention that. Yes. So I have a second class of examples. The second class is rather technical, but I would like to show it to you so you see what kind of other examples you can expect. So this is basically the simplest non-trivial class I could think of, and it's just one ordinary differential equation, quasi-linear, of order 1, and one polynomial here and one polynomial here. You would expect some one-dimensional solution set, and you wouldn't expect a solution if A is 0. So for each 0 of A, you lose a solution. But if it's a common 0, if there is a common 0 of A and B, then just the constant is a solution. So there are D constant solutions of the system. And if a common 0 appears with equal multiplicity, then by L'Hopital's rule, you can construct E additional solutions of the system. So in this sense, this polynomial gives you more information than the dimension polynomial because you really see how many solutions there are. Okay. So I wanted to compare solution sets. And yeah, there is this theorem. In all examples you've seen, except for the one I constructed to have aleph naught in it, all the examples didn't have an aleph naught. And actually I had the theorem about the infinite decomposition 2 years before I had the example having the aleph naught. So I spent 2 years constructing this example. So basically on everything there is no aleph naught, and if there is no aleph naught appearing in the counting polynomials, then solution sets contained in each other are equal if and only if they have the same counting polynomial. Yeah, the proof is basically take the algebraic proof. If there is aleph naught, you can still show that solution sets are not equal under nice circumstances, because a countable infinite set is larger than a finite set, and it's smaller than an affine 1 space. And so you estimate this aleph naught against a constant or against infinity. And if the counting polynomials still are not equal, then the solution sets are not equal. Of course, you have to make this formal, but this is not really a problem. So why do I need this additional information? Because the dimension polynomial cannot capture everything that happens with complete solution sets or not. And I have one example prepared for this. So I take one ODE in two unknown functions, v and u. The dimension polynomial is L plus 2, so there is only one prime component, using the low power theorem here on u. So v is completely arbitrary, and there should be one coefficient for u. What does Maple return? Maple returns that v is arbitrary, and for u we get a new constant a. So this is basically what you would expect by looking at the dimension polynomial. L plus 2 free coefficients. If I compute the counting polynomial of this set of solutions given by Maple, then of course it has L plus 2 free coefficients, but the zeroth coefficient of v cannot be 0, so otherwise we have some problem with this integral. So actually it's infinity power L plus 1 times infinity minus 1, because the zeroth coefficient cannot be 0. Okay, but what's the counting polynomial of the differential equation? Yeah, the first two terms look the same, but there are two additional terms. So there are more formal power series solutions than the ones found by Maple. It's actually quite surprising, because if you look at this set of solutions, you would just expect that it's e to the 1 divided by v. But there are more formal power series solutions. Not all of them are locally convergent, but a non-null set of these solutions is locally convergent. So there are solutions that that were missed by Maple and that you didn't find out with the dimension polynomial.
So Maple only counts which solutions?
Maple finds this set of solutions. V arbitrary and u is given by this formula.
So the difference is that in the bottom one you're taking all the formal power series solutions.
Yes, so this is just the counting polynomial of the set returned by Maple, and this is the complete differential counting polynomial. And there you see some discrepancy. And so I hope with this example I have convinced you that in addition to the dimension polynomial might be useful in some cases. And I'll finish my talk. Thank you for your attention.
Questions? Comments? I have some questions. So, is it true that you have an algorithm to compute your polynomial, but it doesn't stop sometimes?
It usually won't stop.
I don't understand what means usually.
No, there was just some. First, you can show that there cannot be an algorithm to even decide whether there exist formal power series solutions for linear partial differential equations. This is an old result by, when was it? I don't recall the names, it's from the 80s, I can give you the reference. So if you cannot even decide whether there exists a solution, then you cannot count them. So you cannot decide whether the counting polynomial is 0 or non-zero. But I have some means of computing it by hand, and these means are just looking at the formal power series solutions, finding some order in them, and proving by induction how you get a counting polynomial. But this is not algorithmic.
But is there an algorithm that decides, given an equation, that you can do your computation?
No.
It doesn't exist, or you just don't know?
There cannot be an algorithm
that decides whether you can do your computation.
Oh, no. I didn't think of that. No, I don't know.
So that is, so some person who is solving applied problems comes up with a system, person wants to solve it, and the question is it a good idea to apply your methods?
Yes.
Will they lead to anywhere?
So
you can plug it into?
Yes. In many applied settings, this is your theorem. So in basically any applied setting I've seen, you have a semi-linear differential equation. You know all constraints, so you have coherence, and then this theorem applies and you are through.
Your last example. So it seems very clear that this ODE has two-setting solution. If v not equal to 0, then it's this solution, right?
Yes.
If v equal to 0, then you also become 0. So how do you explain your counting polynomial in terms of the solution?
Yeah, this is so the best way I have to interpret this is using the theory by Cartan, Kayla, or Bessier distributions on using the jet space. Because if v is non-zero, but the zeroth coefficient of v is 0, then you find these additional solutions. There you have an irregular singularity in the Bessier distribution over this point. And there you have additional solutions. I don't know of a theorem that tells you that this happens. I only know that over irregular singular points, basically anything can happen. And in this case, you have solutions. I don't know whether there's a theoretic result that tells you why this happens. I had to compute it. And this is rather a tedious computation going over 2 or 3 pages.
But in any case, the computations that you perform, do they all have to be by hand, or at least parts of it can be programmed?
So I use my implementation to get far, and I use some scripts to compute power series solutions up to a certain order. But at some point, I just have to say it goes on the same way as it did before. And I don't know of an algorithm that tells me that this power series solutions extends to infinity, and there I have to do an induction by hand sooner or later.
Any other questions? You have a question?
I guess I can ask one last thing. So what you did really only counts the number of power series solving the system,
yes.
right? I mean, so can you say something about what you're considering, just like, some solutions in some other field, not only like the field of analytic functions, right? It's like can you count also in other extensions of that? I mean, or this is really particular of.
I think that this is really particular because if you look at fields, you basically throw away every invariant or description you have except for something coming from the dimension. Because if you go to the field, you only have your transcendence degree left. Or perhaps the degree of the algebraic extensions upon the transcendence degree.
Another question?
Did you look at any connection with Cartan-Kilder theorem for differential geometry, which tells, given an equation, it tells how many functions or how many variables you generate solutions depends on?
So the best I can give you out of my head is the following. This is even given by the dimension polynomial. If you have n independent variables, the dimension polynomial I think has n plus 1, possibly 3 coefficients. And there are only n Cartan characters. And so the dimension polynomial actually generalizes the Cartan characters because the Cartan characters in a sense contain the same dimension as looking how many free coefficients there are in any order. And the dimension polynomial looks up to that order. And this up to gives you 1 additional coefficient. Was this your question?
Yeah, and I know that there are some implementations even of Cartan-Kilder theorem. Do they give the same?
I didn't try them on too many examples. I think I tried them on a handful of examples, and there they gave what I expected that they should give from the dimension polynomial.
More questions, comments? All right, thank you very much again.